Hi, my name's Ethan. I am a scientist at the Washington Department of Natural Resources. The work that I'll be presenting here, I did with other scientists at the DNR, including Allison Bailey, who's here with us today. So to kind of go over, the project is we're trying to create classification models that kind of predict whether an area of our managed lands falls within a certain forest class, which is called structurally complex forest, which we'll talk about what that is in a moment. The DNR has these, a remote sensed inventory. So we have 10th acre pixels that are predicting different types of forest attributes like trees per acre and height and things like that. So we're gonna try to create models using some of that data. We also went out and earlier this year collected a bunch of field data. So we sent people out, they walked into the woods, they are trained to know what a stand development stage is, which we'll talk about in a second. They made a call and took that GPS point. So we have a data set that we're going to use. And we want our detections after we create and characterize our model. We want to apply it to our land base, and we want the predictions to be at the same scale as the inventory, which is a 10th acre. And we want to come up with a rough pipeline that is not a huge lift to refit and do every year or so. So I'll talk briefly about kind of what is a stand development stage. Well, the way that we're defining that here is kind of almost like a little bit of a life cycle of the forest. You can see you have maybe stand initiation where you have a bunch of very baby trees, and then the stand gets older and it goes through these different cycles. Eventually you kind of get to the pioneer cohort loss where some of the trees start to pass away and the shade dominant trees come back up into the canopy. And we are not necessarily interested in making an 8-stage model. We're mostly interested in, all right, kind of this line between maturation 1 and maturation 2. Can we build a 2-class model? So we went out into the field and it was the winter time. So we ended up collecting a little bit of a biased sample. It would have been great if we had maybe more time. We did the data collection in 2 months. When we go and collect our field plots, like in Eastern Washington, as an example, in Eastern Washington, we collected 2,000 inventory plots on the ground over the last 10 years. For this project, we went and collected about 2,000 plots over 2 months. And so because it was the winter time and we wanted to get to places where it was easily accessible, maybe there's a road there, it's not a perfect, unbiased design. It is biased by there's not snow there and I can get to it easily. So that will influence the kind of models that we can build with it. So I'm maybe planting that now because I'm going to talk about it later. And so when someone goes into the field, they've been trained, they know what a stand development stage is, they walk into a point and they kind of look around at the forest and they maybe are assessing within a 2.5 acre circle whether they believe that location to be a certain development stage, and then they collect the GPS point. And so we had all this data. In the end, we had about 2,200 points that we could use for model building. I maybe have told some of the other people here, I don't know GIS very well. I know how to use it well enough to get the wrong answer. So thank goodness for Allison. She did all of the GIS work and it improved our algorithms. So very thankful for her help. This image here is kind of showing we have a plot center. We are going in and kind of buffering. There's a little circle around where the people would have been looking to make their call. And you can see these kind of little squares, and that's, we have all of these 10th acre pixels, and that's our remote sensed inventory. So we are interested in extracting the remote sensed estimates within these circles. But we also don't want to consider roads, right? I'm not interested in the forest attribute of the road. I'm not interested in the forest attribute of the water. They don't have forest attributes. And we have these, again, like I was saying, resource inventory units, where there are these polygons where there's supposed to be kind of uniform tree attributes. Those are kind of hand-drawn by people within our group, and there are thousands of them. But we want to, if you're in a plot or you're in an RIU, we want to make sure that we're not taking data from a neighboring RIU. So that's why some of these circles turn into not circles. We're not interested in pulling out the 30-some remote sensed forest inventory variables that we have and giving every variable to our model. So we don't need to maybe necessarily worry about, like, basal area and QMD are highly correlated with each other. They're highly correlated with height. So we don't need to feed them all these variables. In fact, we can just pull out things that aren't highly correlated with each other. So when we're thinking about variables that we would want to even give to the model, we want RS-FRIS. We have this remote sensed inventory that comes from photogrammetry, which is largely height-based. So certain things that are highly correlated between our remote sensed inventory and then a ground plot where we're counting up all the trees are things related to height, maybe related to cover, things like that. So we don't necessarily want to use things that are under the canopy. The remote sensing can't see it, so there's a low correlation between the remote sensing and the plots that we would have from the tree list. So yeah, we want the variables to be highly correlated with the ground truth. We also can look at the literature. We are not the first people who've done this. So yeah, let's look for some of those variables. We also want low correlation between the variables, which is what this kind of heat map is showing. And maybe most importantly, we want to select variables that separate these classes of this is structurally complex forest, this is not structurally complex forest. And then we build the models. So the first thing, kind of going back to how well does a variable separate the class of structurally complex or not structurally complex? I'm going to do a single variable logistic regression. So I'm going in, I've got my data, it's been pre-processed. I give a single variable to separate the question, is it structurally complex or not? And then I'm showing the mean accuracy here. And you can see that some variables do better than others, right? Like canopy layers does pretty well, right? And QMD6, that's the quadratic mean diameter of trees with larger diameter than 6 inches. And so trees that have a diameter larger than 6 inches are also very tall. That's kind of your height metric. And so we can use these two to build models. Now, again, I'm going to kind of go back to what I was talking about with, we have a little bit of a biased data set. We did not totally randomly distribute our points. They're not, they were easily accessible and, there wasn't snow there. So instead of maybe, if you had a data set that was unbiased, you could kind of go, oh, I have this many points that are structurally complex, and that's kind of my answer, maybe. And you could use that, that proportion to influence maybe the thresholds. And you could split up your training and testing data set into that same proportion. We can't do that. So we have to maybe ask a different question. What does structurally complex forest look like? What does not structurally complex forest look like? And so what we're going to do is make sure that the training and the testing sets are the same size, and we're going to go in there and we're going to randomly sample a bunch of times. This is kind of, it's similar to your cross-validation. And what this GIF is showing is the hyperplane or the threshold that I'm calculating each time. It's good that it's not shifting too much. If it were shifting a bunch, maybe it would be unstable, right? Every time I'm randomly sampling, coming up with a model. If that line was shifting all over the place, maybe these are not good variables. Maybe it's not a great model. So in the end, I'll be able to get some mean coefficients from my 2-feature logistic regression at this point, and how those are varying. So, and this is a little bit of a summary, but we have these 2.5 acre plot polygons. We have estimates for QMD6 and canopy layers within those plot polygons. We're kind of taking the average for canopy layers, QMD6. We've, done our training and testing over and over again. We've have these mean parameters, and here it is in 2D space, and there's that line. That's like our mean line. What's it mean? Great question. You can see there's some overlap, right? There are complex points that are on the wrong side of that line. And there's some, you can't see them maybe because of transparency, but there are not complex points that are also on that wrong side of the line. So it's not a totally separable problem. But you're more than likely, if you have more canopy layers and are large in quadratic mean diameter, more likely to be structurally complex. And our final detector had a balanced accuracy of about 81 plus or minus 1%. The nice thing, there are more complicated ways that you can do this. And it's almost tempting to get a better answer. And the reason that we didn't do that is, we have these, there was this ask to do this project to quantify on our land base the amount of structurally complex forest. And the data set, even though it's 2,000 points, we're about to apply it to 2 million acres or more. And we probably don't have, like, our sample that we did might not represent what the entirety of the land base looks like. And so we really do not want to overfit a solution and then apply it to the land base. So we're making just the worst model we can, but it works so consistently. That's what we're going for. Maybe I'm saying that in a way that I'm just trying to be funny. Maybe it's a little flippant. I apologize. But yeah, you want something that works consistent. You don't want to overfit, which is what I'm trying to avoid. And there is a, with some of the nonlinear models, the regression trees and things like that, there's a possibility that we could fit on the noise. And I just, wanted to go simple. All right. So now we've got models. We've got these coefficients. We can apply them to the land base. Well, how are we going to apply them to the land base? We're going to use a sliding window. So kind of going back, we want everything to be at the same scale as our forest inventory. However, the models were trained at 2.5 acres. So what we can do is kind of take our model on a walk through the forest. So we have all of these pixels. We have a circle around those pixels. We go, all right, I'm here. I'm looking at all the pixels around me. Nice. I'm taking the average. I'm seeing where does it fall within that QMD canopy layer space, and I get a probability of the class that it's in. And then I move over 1 pixel, and I do it all again. I do this over millions of acres. And because we don't want it to take a long period of time, we also parallel process this because we don't want to wait around forever for the answer. Now, you get a probability. Maybe you can use whatever threshold you want for whether something is in a class or not. But maybe you would be interested in using 50%. And if you were to do that, we can see here in the little red box that we get about 27% of our land base is structurally complex. And, you know, that's great. But you can also see that if I used a different threshold, right, maybe 70 to 100%, the acreage decreases. But also, because we saw some of that overlap, maybe my confidence in that structural complexity can also change. You know, so which one do you choose? You ask your boss. These things have implications, you know. So we asked our boss, and they were like, well, we want to preserve balanced accuracy, right? We want a model that is like equally good at predicting not structurally complex as it is with structural complexity, right? We don't want to show any kind of favoritism. And so here I'm showing like how the balanced accuracy is changing as I'm adjusting that probability. And I can show that like, yeah, there's 50, but if I move over a little bit, maybe to 60, I can kind of preserve my balanced accuracy, how well I'm performing. And then the other ask was, we'd like you to reduce false positives, right? The idea that I'm saying that it's structurally complex, but it's not. It's actually not. So you can see as I move that threshold over to the right, false positives are decreasing. So nice. You can make up your own algorithm if you want to about how to do this. Or you could use J statistics or F scores, whatever you like. So we tried to preserve balanced accuracy while also decreasing false positives. We kind of found like, instead of using 50%, we could use 0.56. And everyone rejoiced. So here's an example. So the maps that have been made here, they're kind of showing we've got the detector, we've got kind of the probability threshold that we want, and we're applying it to the land base. And shown here, anything below kind of that threshold is just been made clear. It's just a little easier to view that way. And what you can kind of see is you can almost see where the water is. You can almost see where the water is, and that means that our habitat conservation plan is maybe working. We don't harvest as heavily in those areas, and in some areas we preserve it almost altogether. And so you see the darker orange is a higher probability that something is structurally complex, and this is just a visual showing that. We also want to compare, you don't want to just go, yep, I did this and we're done. It works, great. We also want to compare with other things. So we compared it with GNN, which is kind of what the Forest Service uses. And we see that on our the managed lands that the state manages, the GNN and the detectors that we have are getting a reasonably similar answer. We're about a percentage off in terms of acreage, which is good. And those are, again, separate data sets, separate inputs. All right, time is up. Conclusions, we're right almost 4 out of 5 times. We're close with GNN, and we accomplished the project goals. Any questions?